MEI Statistics Minor chi-squared tests. 1.2 chi-squared test for a contingency table. So we recall the example from the last video. We were looking at whether there was an association between eye colour and hair colour. So we want to investigate whether these two variables are linked in any way. More formally, we want to test whether the two variables are independent. And precisely, we want to test whether the events of having blue, brown, green or other coloured eyes are independent of the events of having black, blonde, brown, red or other coloured hair. So naturally our test will require hypotheses. As standard, the null hypothesis is that there's nothing out of the ordinary. Everything is as expected, no association. So we present H0 as no association between eye colour and hair colour, or eye colour and hair colour are independent. Note that we do not use the word correlation. The alternative hypothesis is either some association between eye colour and hair colour, or eye colour and hair colour are not independent. I would stick with not independent because dependent has a subtly different connotation that is not what we mean here. We also need to declare our significance level before we start. It is bad form to do so otherwise, because otherwise you could just choose the significance level to prove whatever you want it to do. That's bad statistics. The significance level should be given in the question, otherwise default to 5%. I am going to test at the 5% level of significance. So, as with all hypothesis tests, we assume that H0 is true and find a measure of the likeliness of the observed value occurring purely by chance. Now, the chi-squared distribution is a continuous distribution with a single parameter, that is the Greek letter nu. It's a bit like a V, but it tends to be drawn with one straight edge and one curved edge. And a chi-squared distribution is defined as the sum of the squares of nu independent standard normal random variables. Quite a mouthful. Symbolically, it's a bit clearer, I think. So if z1 up to z nu are distributed normally with a mean of 0 and a variance of 1, so the standardized normal distribution, then the chi-squared distribution with parameter nu is the sum of the squares of all the z's. It is this chi-squared distribution that we'll be using to evaluate the likelihood of our test statistic. This information is not in the spec. So from the last video, we had our observed values and we calculated our expected values. Now, there are some requirements for the test. It loses accuracy when expected values are very low. So if they are low, the rule of thumb you should use is that if they're less than 5, we need to pool categories sensibly in order to raise the expected value above 5. So what do I mean by sensibly? Well, here the values that need attention are these two that I've highlighted. You may be tempted to combine these two columns, the 1 to 3 and the 7 to 9. But that's not sensible because we want to distinguish between high grades and low grades. So if we did want to pool GCSE grades, the most sensible way would be possibly to pool 4 and 6 with 7 and 9 and 1 to 3 with other. However, a more efficient way of doing it would be to pool the brown eye colour with the other eye colour. Now in our example, we have got two problem categories, here and here. We could feasibly pool blonde and red, although we probably want to tell the difference between these two. So I think I'm going to pool other with another eye colour. I'm going to pick green because it has the next lowest expected value and also the lowest total. We simply add the values in the observed and expected tables when pooling. The test statistic, chi-squared, is defined as the sum of the observed minus expected value squared, just like the variance, divided by the expected, and that is to scale the error. Or as it appears in the formula book, frequency of observed minus frequency of expected, all squared over frequency of expected. I personally prefer the former, and that is the one I'm going to be using. So, for the blue eyes, black hair, my observed minus expected squared divided by expected, I simply plug in the values from the table. 7 minus 8.19 squared divided by 8.19, which equals 0.173 to 3 decimal places. I then put that value into a new table called the contributions to the test statistic. I then continue next doing blue and blonde to fill in this table here. I should also mention that again you should round to decimal places, not significant figures, so the accuracy is consistent throughout. Now remember, our test statistic is the sum of all those values, so we simply add them up. And so our test statistic equals 11.903. In order to find the critical value, we need to find the value of nu, and that represents the degrees of freedom of the contingency table. This is defined as the number of variables that have the freedom to vary. In order to calculate our expected values, we used these totals. So these totals are set in place. So if I was looking at black hair and say the first one was 10, that has freedom to vary. If the second one was also 10, that has freedom to vary. But because this total is set in place, the only possibility for this one is 9, so that does not have freedom to vary. Similarly for blue eyes, if this was 10, this was 10, this was 5, this was 5, the total so far is 30, so the only option left for this total is 7. So that does not have freedom to vary. So these all have freedom to vary. These in the final row and final column do not have freedom to vary. Here, nu is equal to 8. So for a contingency table, the value of nu, the degrees of freedom, is the product of the rows minus 1 times the columns minus 1. So this is what our formula book looks like for the critical values. It's got a sketch of the chi-squared distribution, and close to 0, this is no association, and up the x-axis, this is lots of association. Now because we're always testing for lots of association, because our H0 is down here, this means that all of our chi-square tests are one-tailed, and they are right-tailed tests. This means that the left-hand side of this table is a big red herring that is no use to you. Now we recall that we were using the 5% significance level, so we find 5% in the table. Our value of nu is 8, so we go along 8 and down 5 until we find our critical value of 15.51. And there are many graphical calculators that can also do this calculation for you. So if our test statistic is 11.903 and our critical value is 15.51, that puts 15.51 at this line, and our test statistic 11.903 is in this region, so that is not significant. So we accept H0. and our conclusion is that there is insufficient evidence to suggest that there is an association between eye colour and hair colour. That conclusion should never be definite in conclusion, and note that there is not evidence that there is no association. There is simply insufficient evidence to suggest that there is an association. That is an important point. In the next video, we're going to be looking at goodness of fit.